All right, so we're going to go through the Unit 5 study guide here. So for our first question, it says, given the reaction, the following data was collected as the N2O4 reacted and formed NO2. Fill in the missing values. So N2O4 is on the reactant side of our equation, and then on the right side we have NO2, but I want you to notice that it is going to be produced by a factor of 2 compared to the N2O4. All right, so at time of 0, our initial time, all of the concentration is N2O4. We don't have any NO2 produced. So we're going to look at the difference between time of 0 and time of 100. So here, the concentration goes down by 0.05. Okay, but on the NO2 side, so it's going to, the N2O4 is going to go down and the NO2 is going to increase by that amount, but by a factor of 2. Okay, so let me pull up my calculator here. Okay. All right, so we've got 0.05 and it's going to increase by a factor of 2. So the difference will be 0.1. Okay. Now we're going to look at the difference between 0 and 200. So at this point, our concentration has decreased by 0.075 on the N2O4 side, and NO2 will be produced, but by a factor of 2, so the concentration will be 0.15. Okay. Now we're going to look at 0 to 300. So 0.2 minus 0.1125. So that's how much the N2O4 is going down by, and then produced, we're going to have 0.175. Of our NO2. And then finally, our last time interval, and then multiply that by 2, 0.1874. All right, moving down to number 2. Okay, so for number 2, it says, consider the reaction. Several experiments were conducted and the data is shown below. First question says, what is the reaction order with respect to carbon monoxide? So when we're trying to look at the reaction order for carbon monoxide, we want to essentially rule out the nitrogen trioxide. So we want to find 2 experiments where the concentration of nitrogen trioxide doesn't change. So between experiments 2 and 3, the concentration of nitrogen trioxide doesn't change. So this will allow us to just look at the carbon monoxide. Okay. So between 2 and 3, we're going to look at the rate of experiment 2, and we're going to compare that to the rate of experiment 3. Okay, so for experiment 2, we have the constant here, and then the concentration of CO is 0.12. We're going to raise that to the N. And then we have NO3, which is 0.36, and that'll be raised to the M. And then rate 3, we have K. In experiment 3, the rate for carbon monoxide was 0.03. And then for experiment 3, NO3 was 0.36. Okay, so here the rates are going to cancel out for NO3, and then our rate constant is going to cancel out here. So we'll be left with So I should say, if I plug in my values now for the rates, the rate of experiment 2 was 8.40 times 10 to the minus 3. And then the rate of experiment 3 is 2.10 times 10 to the minus 3. And then we're going to plug in values for, or I guess we're going to carry over, I should say, our concentration. So for CO, we have 0.12. And then for CO experiment 3, we have 0.03. There we go. Okay. So when we plug this into our calculator, this will simplify down to, on the left side, with our rates, it'll be 4. Okay, and then 0.12 divided by 0.03 ends up being 4 as well. And then that's raised to the n. So to make this work, n would have to be 1, and that will tell us that it is first order. All right, we're going to do the same thing for NO3. We're going to find 2 experiments where CO doesn't change. So if you look at the table here, experiments 1 and experiments 2, the concentration of CO doesn't change. So we're going to repeat the process, but we're going to use those 2 experiments. All right, so if you look at this, experiment 1, it's going to go on the top, and then experiment 2 is going to go on the bottom. So we'll have, for experiment 1, K, and then our concentration is 0.12. For NO3, the concentration is 0.72. And then for experiment 2, same thing, K, 0.12 for our CO, and then NO3 is 0.36. All right, so let's plug in our rates now. So we're going to have 1.68 times 10 to the minus 2 over 8.4 times 10 to the minus 3. And when we write out our right side, the constants are going to cancel, and then our concentration of CO is going to go away. So we're just left with 0.72 raised to the m, and then 0.36 raised to the m. So we'll end up with, if we divide the rates, you get 2, and then you should also have, so 0.72 divided by 0.36 is also 2, and that's raised to the m. And to make this work, m would have to be 1, which is first order. All right, let's move down. So it asks us for the overall reaction order. So to get the overall reaction order, we add m plus n, and that is going to be 1 plus 1, and that'll give us 2, which is second order. All right, our rate law for the reaction is going to be rate equals K, and then we have the concentration of CO. All right, it's first order, but we don't have to write the 1, so we'll just leave it like that. And then NO3, which was also first order, so we're just going to go ahead and leave off the 1 there. All right, it says, what is the value of K with units? Okay, so if I were to solve our rate equation for K, I would have K equals, we would have to divide both sides by CO and NO3. So we would have rate over CO and NO3. Okay, so if we plug in, you can pick any of the experiments. I'm just going to go ahead and pick experiment 1. So 1.68 times 10 to the minus 2 over, let's see, we have for CO in experiment 1, it's 0.12, and then for NO3 in experiment 1, 0.72. So if we plug that into our calculator, we get 0.194. And then because this is second order, our units are going to be 1 over m times s. All right. Number 3 says scientists have suggested 2 reaction mechanisms for the reaction. Why is choice B more likely than, or why is choice B a more likely reaction mechanism, and then explain. All right, so the 2 mechanisms differ because the first mechanism, you only have 1 step. In the second mechanism, we have 2 steps. We have a slow and a fast step. So the answer to this is actually quite simple. I know this looks like a lot of information, but if you recall, it's really unlikely that particles are going to collide with enough energy at the right orientation for a single step reaction to occur. So it's more likely that the reaction will occur in multiple steps, like mechanism 2. So I'm just going to kind of write that out. So unlikely a single step will occur because it requires particles to collide with enough energy and the correct orientation. Okay, it says write a predicted rate law for this reaction. So in mechanism 2, the slow step is the first step, so that is going to be our rate determining step. So we're only concerned with the reactants when we write out our rate law. So it's going to be rate equals K, and then it will be the concentration of our iodine and our chlorine here, and then our H2. That's it. There's no coefficients, so we don't need any exponents. All right. Number 4 says, on the graph below, draw a reaction profile diagram to illustrate the following reaction. All right. Well, it tells us in our question or in our reaction that delta H is negative. So when delta H is negative, that means that it's going to be an exothermic reaction. So that means that our reactants and our products are going to differ in energy, in that the products are going to have less energy than the reactants because heat energy has been released into the surroundings. Okay, so our reaction profile will look something like that. I'm just kind of sketching it out here. And I'm just going to go ahead and label the different parts. The question doesn't ask us to do that, but I'm just going to go ahead and label the parts here. So these are going to be our reactants. These are going to be our products. And I'm just going to kind of dash the line over here to the products. So the difference in energy between the products and the reactants is our delta H. EA is our activation energy. So for the forward reaction, that would be our activation energy. And this dot at the top is our transition state. Okay, moving right along. Okay, number 5 says the rate law for the reaction between hydrogen gas and nitric oxide is experimentally determined to be rate equals KH2NO2 to the second. Which mechanism below could be a valid mechanism for this reaction? Justify your answer. All right, so we have two mechanisms. In both mechanisms, the first step is the slow step. So we are going to use that first step only to write out our rate laws. And we're just going to look and see which rate law would match the rate law that's given in the question. So for the first mechanism, we have rate equals K. We have the concentration of H2. And then we have 2 NO, so it'll be NO, and then because of that coefficient, the 2 is going to go up here. And then for the second mechanism, we have rate equals K. We have H2, and there is not a coefficient, so the second piece here will be just NO. And if you look, mechanism 1 matches our mechanism that's given in the, or sorry, not the mechanism, the rate that's given in our question. So that would be the answer. Okay, 6 says, given the following two-step mechanism, identify the intermediate, what's the overall reaction, and then there's a couple other questions. All right, so remember, an intermediate is going to be produced in the reaction, and then it's going to be consumed. So it doesn't show up in the products, our final products. So we have this reaction, and in the reaction, our product here is ClNO2. In the first step, we have ClNO2 that's produced, and then we also have chlorine that's produced. So it can't be this because that is one of our final products. Okay. Now chlorine shows up as a product in our first step, and then chlorine also shows up as a reactant in our second step. So the chlorine is produced in the first step, and then it's consumed in the second step. So that is the definition of an intermediate. So our answer would be chlorine. What is the overall reaction? So when we write out our overall reaction, we are going to just eliminate anything that exists on both sides. So chlorine being our intermediate will be eliminated from the overall reaction because it exists on both sides. So if I draw a line here, it exists on both sides. And that's the only thing. So our overall reaction will be NO2, and we have 2 of them here. So it'll be 2NO2, and then Cl2, and that's going to produce, we have 2 of these, so it'll be 2ClNO2 gas. Okay, if the first step is the slow step, what is the rate law? So it doesn't tell us what the fast and the slow step are. So let's just assume that the first step is the slow step. So if we do that, we're just going to write out the rate law for our reactants, which are right here. So it'll be rate equals K, and then we have NO2, and then Cl2. The second thing it asks us to do is if the second step is the slow step, what is the predicted rate law? So we're just looking at these 2 pieces right here. The rate law for the second step is going to be very similar. Rate equals K. We have NO2. And then instead of Cl2, it's going to be just Cl. Okay, number 7. For the graph shown, answer the following steps. Is the overall reaction endothermic or exothermic. So if we look at our diagram here, our reactants are starting with this amount of energy, and then our products are finishing with energy that's lower. So that is exothermic. Endothermic, I'm going to write this up here. Endothermic is where you have more energy than what you started with. All right, so how many steps take place in this reaction? So we have 3 different transition states. So they're going to be 3 steps. Is step 1 endothermic or exothermic? So step 1 starts here and ends with more energy. So that would be endothermic. D says, which step is the slow step? Okay, so this one, we're going to compare the activation energies. So for the first one, we're going from here all the way up to here. For the second one, we're going here up to here. And then for the third step, we're going here up to here. So clearly, the first step has the most activation energy needed. So that is going to be the slow step. All right. On the graph below, draw a reaction profile of a reaction with the following. So the reactants are at 60. I'm just going to draw a flat line here. Transition state is at 90. So let me go ahead and we'll just put that, let's say here. And then the products are at 10, which is down here. All right, so let's go ahead and just kind of connect the dots here. Okay, I'm going to go ahead and label these. So we have reactants, products, and up here, this is our transition state. All right, so it says, now add a dotted line that represents a catalyzed reaction that occurs in 2 steps. The energy of the first transition state is 75 kilojoules. So our transition state for the first original reaction, I should say, was 90, so we want to find 75, which is here. It releases 40 kilojoules of energy, so it doesn't tell us where to draw it. We're going to have to do a little bit of math here. So let's see, 75, 65, 55, 45, and then we're going to have 35 down here. Oops. So let's just move that over just a little bit here. Okay, so that's our transition state. And then it says the energy for the second transition state is 50. All right, so we're going to bump up to, let's say, I don't want to draw this on top of the other one. Oops. Let's put it at 50 here. Okay, so we'll go up to our first transition state. We'll go down to there, we'll pop up to here, and then we'll finish, finish down here. So this is transition state 1, this is transition state 2, and there you go. And that is the study guide. Wow, that was so much fun.